Diamond is a very pretty, sparkly material. It makes a wonderful addition to jewellery, or a terrible addition to a billionaire's phone case. But being sparkly isn't actually the most interesting property of diamond. Diamond is in fact harder, faster, stronger, and even in fact slipperier than all other materials. Being better at nearly everything makes diamond really useful for all sorts of tech and sciencey purposes. I'm Tom, and welcome to Physics Foundry. First of all, before we go into diamond's crazy properties, what is diamond? Amazingly, it's made up of exactly the same thing that makes up your pencil lead, carbon. The difference between the graphite of your pencil lead and diamond is in how the carbon atoms are structured. Atoms in graphite are sheets of hexagons with weak bonds between neighbouring sheets. This means you can easily knock chunks off to write with, or, as Manchester University's Andre Geim did, peel off a single atom-thick layer, realise it has cool properties, experiment with it, and get awarded a Nobel Prize. Diamond has a much stronger structure, with none of the weak bonds associated with graphite. The way that diamond is made up of millions of these strong, simple, regular cubes is what gives diamond all of its crazy properties. So let's get on to what diamond can do. There is not a single material in existence which is harder than diamond. So it's fairly easy to see why really heavy-duty drill bits, circular saws and other cutting instruments often use diamond on their cutting edges. Because diamond can cut into any other material, one of the standard tests for hardness is actually just to scratch the sample with a piece of diamond and see how badly the sample is damaged. Both sound and heat travel faster through diamond than in any other material, which is actually a lot more cool than it sounds. In fact, diamond isn't just a little bit better at spreading heat. Copper, well known as a conductor of heat, is about 5 times worse. You can see just how good diamond is if I pick up this crystal of diamond and just rest it on top of this ice cube. The heat from my fingers travelled really quickly through the diamond and cut straight into this ice without me putting any pressure on it. And how is this useful? Well, here in the physics department, diamond is often used to smooth out the temperature of laser beams so they don't break, or to help cool down equipment that needs to be really cold to work. Closer to home, computers also work better when they're cooled. So although the computer you're watching on now probably doesn't have diamond to disperse heat, there are crazy expensive computers that do. You might think that because you can shatter diamond with a hammer, it's actually not that strong. But diamond is strong where it counts, flexural strength. This means you can vibrate it really fast without the sample breaking. And of course it goes without saying that diamond's flexural strength surpasses that of any other material. The most common application of this is in MEMS, micro-electromechanical systems, devices hundreds or thousands of a millimetre in size, which convert from movement to electrical signals, or the other way around. It's these devices that tell your smartphone which way up it's facing, and airbags when to deploy. The microphone in your phone will also use a MEMS to convert from the sound of your voice into an electrical signal, as will a microphone in pretty much any other portable device. It may sound strange, but depending on the surface treatment, diamond can be up to 4 times as slippery as Teflon, the stuff that coats frying pans. This means that pretty much any technology that involves moving parts, such as a spinning disk inside the hard drive of your computer, can be made to run more efficiently and last longer if coated with a really thin layer of diamond. Of course, not every device uses diamond because it's expensive, but it's interesting to note that most of the diamond used in these purposes is man-made, which is a lot cheaper than naturally found diamond. So how do we make the shiny material? Well, to answer that question, I'll pass you over to Dr. Ollie Williams, who grows diamonds here at Cardiff University.
The principal difference between diamond and graphite is within the bonding structure. In nature, carbon would rather be bonded in the graphite structure at the pressure and temperature that we're standing now. So on the Earth, if carbon is to grow into a structure, it will grow into a predominantly graphite kind of structure, not into a diamond structure. Now, I think it's commonly known that diamonds are mined, which means they come from the ground, and they actually come from very deep within the Earth. And there's a hint there, because in these conditions you have very, very high pressures and temperatures. Now, to put a perspective on that, we're talking about 150 kilometers below the surface of the Earth. So the pressures are about 100,000 bar. Now, we're actually standing now at 1 bar pressure, so it's 100,000 times greater than the pressure we're standing at now. And to put it in perspective, the only other place on the Earth anywhere near this is the bottom of the Marianas Trench in the ocean, which is 100 times less pressure than this. So these are really extreme conditions. The temperature is also about 2,000 degrees C. And under these conditions, you can grow diamond very, very slowly. I mean, these diamonds grow over millions of years. So it's a slow process, not very practical in the laboratory. You can reproduce these conditions in the lab, but they're slow and they're very difficult to control. They're also rather dangerous. So in the laboratory in Cardiff, we do a very different process. we actually do something called chemical vapor deposition. And within this process, we don't actually need the high pressure to do this. So it's a little bit of a trick because we're kind of cheating nature. Normally we should get graphite when we do this. But I'll kind of explain as I go along why this happens. So what we do is we take an airtight vessel. So you just think of anything that's airtight, and we pump all the air out. So there's now a vacuum in this chamber. And then we flow into this chamber some gases, mostly hydrogen. So it's 99% hydrogen and about 1% methane. Now, if you remember, methane is CH4, so it's carbon with 4 hydrogen atoms. So that is my source of carbon. It's within the methane. Now, if you were just to heat this up in the chamber, you'd get horrible black stuff all over the walls. It would be basically graphite, like soot in your fireplace or anything like that. So we can't do that. So what we actually do is we hit it with very high power microwaves. So if you think of your microwave oven in your kitchen, it's about 700 watts, probably, something like that. But it's designed to cook all over the oven. In our system, we're actually focusing the microwaves in one point. And on top of that, we're using a very big oven. We're using about 6,000 watts. So when we do that, we hit the gases, they get superheated. They get extremely hot to about 3,000 degrees C. Now, under these conditions, you actually form what's called a plasma, which is the fourth state of matter. So if you heat a solid, you get a liquid. If you heat a liquid, you get a gas. If you heat a gas a lot, you get a plasma, where they can actually become ionized. And it's within these special conditions that we can grow diamond. The plasma generates our growth source, which is the carbon atoms, and we have another thing called atomic hydrogen, which is just a very aggressive etching machine. So when the material grows, we actually grow both diamond and graphite, but we're etching back the graphite because it cannot resist the atomic hydrogen. Now, you know how strong diamond is. It's able to resist this. So you have a very unusual growth conditions where we sort of trick nature by allowing both conditions to grow but etching one back. And that's pretty much how CVD works. So there are a number of reasons why we developed CVD. It's been around for about 30 years. And the principal reason is we're able to control the diamond growth much better than nature can. I mean, nature is actually a pretty poor diamond grower, and there's a good reason for that. You can imagine within the earth, you have all these sort of material around. You don't have any control over it. Of course, no one's actually trying to control it. It's just the earth. So you have a lot of impurities in diamond, and that's what gives them color. So yellow diamonds have a little bit of nitrogen in them. Blue diamonds actually have a little bit of boron in them. Now, in our gas system, I already told you, we pump all this sort of air out. So all that's there is a vacuum. So when we start to grow, it's whatever we put in there, we determine the conditions of the growth. And this means that we can make blue diamonds. We can make better ones than nature because we have very pure conditions. We can make yellow diamonds. We can control the electronic properties of diamonds very carefully by adding very small amounts of different material. And we can also grow much, much higher purity diamonds than you'll ever discover in nature. So to put it in perspective, I mean, we're able, well, maybe not myself, but there are teams that have demonstrated diamond purities with maybe 1 atom of nitrogen, per billion carbons. That's extreme purity that you will never find in nature.
Any comments, questions, or suggestions, feel free to leave them in the comment section below or on Twitter. And be sure to check us out on Tumblr and Facebook for more cool science.